You made it through the semester almost. Another 48 hours. You'll be done with micro. I just wanted to remind everybody that we've got the last lecture quiz up on Blackboard. Opened it at 8 o'clock this morning, and it'll be open until 11 o'clock tonight. So some of you have already taken that quiz, but just want to remind the rest of you not to forget to do that. And then Thursday, we have our last lecture exam, which will be worth 100 points, right? And that's going to be over chapters 13, 14, and 15. And that'll be open during our normal 1:15 to 2:30 time slot, unless you've communicated with me about a different time. I wanted to also tell you that final grades are due in on the 17th, which is this coming Monday by 5 p.m. My plan is to get the exams corrected before that time, but please don't email me Friday morning at 10 o'clock and say, hey, did you get the exams corrected? I'm not going to tell you a time by which I will have them done, but I'm not going to dilly-dally. I'm going to get them done as soon as I can, but I've got some things going on, just like you guys have things going on. So my plan is to email everybody an Excel spreadsheet when I have the exam corrected, and I will list by J number your fourth exam score and your total course points. Okay, so I'll email that to you when I get it finished, and you can assume when you've received that I've also submitted the final course grades into Banner. Okay. Any questions on that? All right. Just making a note to myself so I don't forget. All right. Very good. Any questions on what's going on the next few days with respect to the exam, or how the scores are going to get posted and all that good sort of stuff? Otherwise, we'll open the floor for questions related to chapter 15 or 14 or whatever you would like to ask. I'm sure you've had a chance to take a look by now at chapter 15. I hope so anyway.
The differences between B and T lymphocytes. Let's see. One sec, I should probably actually grab my book out for it before I go any further into that.
You do obviously want to know what those two cells do in terms of the immune response. And I go over that in the Zoom lecture, which actually I reviewed yesterday. I took a look at it just to see, what you guys were looking at, and I think I did a pretty good job. I think I went through and talked about the important role that both of these two cells play in the immune response. But of course, if there's still some confusion, now's the time to ask. I'm assuming you have looked at that Zoom lecture, or you have started looking at the book. This is what I was getting at on that email I sent out last week. You really want to come prepared for these classes as best you can, as opposed to me trying to lecture on them. I've already posted the lecture, so we can use our time to sort of clarify. So Carolina is asking in the chat, slides 56 to 61, do we need to memorize the steps in detail? I'd have to go see what those slides are. Let's pull it up and look. 56 to 61. Can you expand upon that, Carolina, as to what those are? Because I just do not remember. Hello, Carolina. Okay, I don't know if she's not hearing me or what. 56 to 60, what was it? 61 or 2? Can you guys hear me?
It's
She
to
said
61.
Okay,
Yeah.
56 to 61. Thank
And
you.
she put in chat, it's how helper T cells work and the process.
The answer is absolutely yes. Yeah. This is critical to understanding the immune system and the response of the immune cells. You've got to know what helper T cells do. And these slides, what I did basically was I cut and copied this 6 times with the idea that, and you tell me if I'm wasting a lot of valuable storage space in the college servers, but my thinking is when I present this information, I could have just given you this one slide, but I'm thinking like, how would I want this presented if I was a student? Well, I want to present it in a sort of a logical, stepwise, story-wise fashion. At least that's how I learn best. So as you go through these, you can see how each one is just sort of classified or clarified, if you will. It happens in a sequential sort of way. And not only do you have the explanation, of course, on the side, but you have a diagram showing, what's actually happening. So yes, absolutely critical slide this is. And again, if there are questions about any particular aspect of that, let's ask. We go back to the chat, see if she's responded with anything.
Okay.
So I grabbed
Okay.
the wrong book from my laptop.
Questions, other questions? Tell me what you want to go over, what's confusing you.
Could you go over the T helper activation? I think it starts on 39.
Yeah. So let's see. Slide 39. Okay, I'm going to share my screen. You guys see slide 39 here?
Yeah, I can see it.
Okay, great, thanks. All right. I don't know why this is still showing here. Hang on one second. First of all, let me just say this video you should watch 3 or 4 times. It's really good. So before we can talk about how a T helper cell gets activated, we have to understand an important concept, and that is the role that the antigen presenting cell plays. Okay. So this leads up to activation of the helper T cell. So what is an antigen presenting cell? Well, as it mentions in your book, it could be a macrophage. It could be what's called a dendritic cell. Um, and even B cells can sometimes act as antigen presenting cells. But I think of macrophages when I think of an antigen presenting cell. So can anybody tell me basically what this APC does? APC stands for antigen presenting cell. How does it present the antigen? What does it have to do? Anybody?
Isn't it that it has to break it down to a smaller molecule and kind of hand it off?
Yeah, that's a great a metaphor to have or to use. Handing it off, kind of like when you're running a race and the batons are passed from one sprinter to the other or whatever, you know. So this macrophage has to somehow acquire the antigen. Well, what is the antigen? The antigen in this case, we will assume is part of this invading microorganism. Let's pretend it's a bacterium that was introduced into a cut and into your body, and now it's causing an infection or could cause an infection. So all macrophages are famous for their ability to phagocytize, right? They're big, hungry cells. So as you say, they phagocytize, they break down the bacterium, and then they are going to take a part of that bacterium that makes it a non-self cell. It's going to take an antigen, a molecule that was part of the bacterial cell, and then present it on its surface. So the antigen presenting cell, the macrophage, gobbles up the bacterium, breaks it down, kills it, takes a particular antigenic molecule that was part of the bacterium, shown here in blue, okay, the two little blue dots there, and presents it on the surface of what's called a MHC, a class 2 MHC. Does anybody know what MHC stands for?
Major histocompatibility complex.
Exactly, major histocompatibility complex. That's a mouthful, isn't it, Gabby? Yeah, MHC. And so these two little corn dog looking things, I don't know what you describe them as, that's what they remind me of. They are basically, they're taking that antigen and they're presenting it to a helper T cell, which hasn't come into the picture yet here, has it? We're just simply showing what leads up to that interaction between the APC and the helper T cell. All right. Are we all good with that antigen presenting cell? Because that is a very critical thing to understand.
Yes.
Okay. Because without being presented the antigen, could the helper T cell become activated? The answer is clearly no, right? So here comes our helper T cell. This helper T cell has a particular receptor on it called a Cd4 receptor. Okay, all helper T cells have Cd4 receptors on their surface. That's what makes them helper T cells. And here it is docking with the APC. And what we notice is that the receptor here in red or orange, these two guys, they are going to fit into the antigen that's being presented to this cell by the APC. Will all helper T cells be able to do this? Yes or no?
No,
Why not?
because they have to be specific to that particular antigen.
Right. And when you say that, you mean they have to have the specific shaped receptor. I'm sure that's what
Right.
you said or assumed to be saying. Yeah. But good to clarify that. So yes, they have the proper shaped receptor that will recognize that antigen and only that antigen. This gets back to the earlier part of the chapter. clonal expansion, blah, blah, blah. We can talk about that later if you want, but that's exactly right. Okay. Now, let's activate this helper T cell. We haven't quite done it yet. We've docked, we've recognized the antigen as presented by the APC, so that's all well and good, very important. And now what the APC does upon docking with the helper T cell is it releases a particular chemical called interleukin 12. Now, I will and should say something, clarify this right off the bat here. In the preceding chapter, which is what the PowerPoint Zoom lecture was covering, they talked about interleukin 1. They've since modified that and changed the number. So if you watch the Zoom lecture and I don't have interleukin 12 on the PowerPoint in the video lecture, okay, I've got it on the PowerPoint by itself. I've uploaded the latest version. Just make note that there's a minor difference here. So instead of interleukin 1, it's interleukin 12. This production of interleukin 12 by the APC is truly what activates the helper T cell. What does the helper T cell then do? And again, just to stop for just a moment, here's that blown up view of the interaction of the two cells right here, if you want to check that out. The helper T cell, upon activation by the interleukin 12 secreted by the APC, can begin to release interleukins of its own, which can hasten and promote B cell activation. Remember, these are helper T cells, but they work in close concert, don't they, with B cells to construct a response to that antigen, which we'll assume is the enemy. Okay, come up with some silly metaphors, but whatever works. Does that help clarify that?
Yeah, thank you.
Okay. The term cytokine, you've heard of that perhaps, read about that. Cytokines are a general term to describe a bunch of different kind of chemicals, many of which are interleukins. But cytokines, they basically are what help activate B cells. Some cytokines do that. Other cytokines do other things, but they basically are chemicals produced by lymphocytes. Let's see what the definition in the back of the book says under cytokine. Just kind of curious. Cytokine, a chemical substance produced by white blood cells and tissue cells that regulates development, inflammation, and immunity. So it's not strictly immunity, apparently. So regulation can be, or development, I should say, can be influenced or regulated by cytokines, as can the inflammatory response too, which would be, again, innate, as we talked about in chapter 14, right? The inflammatory response is an innate, all-purpose sort of response. Okay. So again, then we talk a little bit about different kinds of CD receptors. We said CD4 were helper T cells, but there's also CD8 receptors. These are on the surface of what are called cytotoxic T cells. Does anybody know how cytotoxic T cells kill other cells, like say virally infected cells or cancer cells? Those are the two cells that cytotoxic T cells generally target.
Is it the perforins? Or
Yeah,
hard to say because they poke holes into it?
Yeah, absolutely right. Right on the money. Yeah, and there's a video I think that I'm sure you watched because you quoted it, poking holes. That's kind of what goes on. These perforins and granzymes. There's a slide here that I show somewhere coming up that describe the action. So as the name sort of implies, cytotoxic they're toxic against the virally infected cell or the cancer cell, the cell that we want to get rid of, right? We want to destroy. Yeah, so again, they are close cousins to helper T cells, right? They're called cytotoxic, and what makes them unique, chemically, is the fact that they have a different sort of receptor on their surface, a CD8 versus CD4. Yeah, they are really, really important cells, cytotoxic T cells. They're the ones, I talked about the hand-to-hand combat in my Zoom lecture. I generally think of T cells as being the infantry, where they're in the trenches doing the hand-to-hand combat. They're interacting directly with the foreign invader, if you will. Well, cytotoxic T cells are the ultimate infantry because they are producing these perforins that literally poke holes. Like a bayonet pokes a hole in somebody. This is a chemical bayonet that pokes holes in cancer cells and virally infected cells, and of course the contents leak out, the cell dies. How about other topics? Generally, what I find
I have a
with
quick.
students is that they get confused with the T and B cell activation. Go ahead.
Oh, it's just from the beginning. I missed it and I went back to try and find the answer and I couldn't. I don't know if we need to know it or not, but it's about the slide that talks about how the lymphocyte receptors and the different antigens. And one of the questions, there was 3 questions on the slide. And the last one said, when, where, and how do the capacity to distinguish self from non-self arise?
It was a slide in the PowerPoint.
Yeah, it was in the beginning.
Okay. This
That
one,
one.
maybe? Is that the one, Steph?
Yes.
Okay. Okay. So these questions are sort of prompting you to think about the complexity of this process. And then we talk a little bit about the answers to these questions. So are you asking me to answer these, or what's the?
Well, just to that last one, like how a basic answer to
Okay.
how
Yeah.
they
So,
do that.
okay. So let's define, and I think we kind of already have a sense of what a self cell versus a non-self cell is. Because if I'm a white blood cell, I'm a macrophage, let's say, I have to have the ability to differentiate between cells that I know could cause further infection, disease, or death of the organism I'm a part of, right? From a healthy, normal cell that's supposed to be there. So the ability of an immune cell to recognize antigen, which is typically or could be a part of a foreign non-self cell, is absolutely critical. But could the non-self molecule that we're talking about, I use the term cell, but could the non-self entity be a toxin produced by a bacterium? The answer is yes. Would the immune system view that toxin as foreign? The answer is what?
Yes.
Yeah. Anything that's going to cause you harm, think of it as a non-self entity. Okay, a toxin, a virus, a virally infected cell, a bacterial cell, anything that could cause you harm would be viewed by the immune system as a non-self, again, I'll use the word entity, because it could be a cell, but it could be a chemical produced by the pathogen, like a toxin, an endotoxin, exotoxin, that kind of thing. Okay, so where, when, and how does this capacity to distinguish self from non-self take place? Well, the first word there, when. When does this capacity begin? Can anybody tell me, just in a sentence? When does the capacity to distinguish self from non-self arise in the immune system?
When you're a baby.
Right, even
Or
before
even
then.
before.
You know, Juliana, this has got to be, if you really seriously think about it, so interesting for you. Being pregnant. I mean, I hope you
Yeah.
think about this stuff because it's very cool stuff.
Oh, for sure.
You're having a boy?
I have no idea. It's a
Oh, you don't know.
surprise.
Okay. It's going to be a surprise. Great.
Yep.
Now, even before your son or daughter is born, he or she is developing the ability to do this. I mean, it's just almost mind-boggling. Even before they've been exposed to antigen, in his or her genes of the cells that will become hematopoietic stem cells in the bone marrow, this process is being laid out. And it's basically some complex genetics. And I cannot get into the detail, nor can I speak intelligently on how this happens, but you have your cells as a fetus developing in mom are laying the groundwork for this ability. So here we talk a little bit about that, the fact that there are the myriads, hundreds of different genes which can be sort of rearranged and shuffled in different sequences that culminates in the ability of resulting white cells to differentiate self from non-self, to be able to differentiate molecules that are part of normal healthy self cells or molecules that are part of non-self potential pathogenic entities. Okay, so that's what we're talking about. So as we said earlier, when we were talking about how the T cell docked with the APC, each of those T cells and B cells that are formed by you have a specific receptor that can recognize one specific unique antigen. So if you are exposed, let's just say, to millions of different antigens in your lifetime, that means you have millions of different white cells, T and B cells specifically, that you formed in your red bone marrow that have the potential capacity to identify all of those different antigens. Okay, so we talk about this process of white blood cell formation. And again, I apologize to some of you who haven't had A&P yet, because boy, oh boy, it's sure beneficial, isn't it, to have A&P before you come into micro. It's not necessary or required, but it's preferred because it gets super complicated if you don't have some basic A&P. So again, just quick review. In the red bone marrow of your bones are these hematopoietic stem cells or hemocytoblasts that differentiate into the formed elements. Those are the red cells, white cells, and platelets, right? And in the case of B cells, they generally do most of their maturation in the bone marrow, while the T cells generally do a lot of their maturation in the thymus, but eventually are released from the bone marrow and released from the thymus, and they can set up shop in the lymph nodes. They can set up shop in GALT, MALT. You know what those are, right? What's GALT? What's MALT? Do you remember that?
Gut-associated lymphoid tissue.
Right, good job. Yeah. So here we're showing, of course, a lymph node, but as the lymph is filtered by the lymph node, these cells are out there looking to identify antigen because they have the proper receptors. So what was the other part of that question? Yeah. I'm gonna, let's see, I don't remember where this next slide is that I'm thinking in my mind. Oh yeah, it's this one. Okay. So here's our stem cell in the bone marrow. It's going to give rise to a B cell or a T cell ultimately. So we don't define B or T, we just say lymphocyte. And as this precursor stem cell differentiates and divides, it's going to give rise to a whole host of different kinds of progeny lymphocytes, each of which, notice, has its own unique receptor site, right? That can respond to a particular antigen. Now, notice that these two guys here that are X'd out are X'd out. Why? Because they have a particular receptor that senses what? Can detect what?
Self.
Well, obviously self. What does that mean? Give me an example of a self cell that these two cells might be able to recognize.
Muscle tissue.
Right, muscle cell, brain cell, kidney cell.
So if they were to be put in active use, then whenever they would see a muscle cell, they would trigger an immune response to it, which you don't want.
Possibly, yeah, that's
Yeah.
exactly right. And so we talk about autoimmune diseases whereby the body attacks itself. You've heard of that, right? Yeah, whereby these particular these cells that are produced just don't undergo apoptosis like they should. Well, what is he talking about? What is apoptosis? Anybody know what that is? Apoptosis, because these guys are undergoing apoptosis.
Cell suicide, basically.
Exactly right, Samuel. Exactly right. They're committing hara-kiri. Isn't that the term they used to use? Right? Take the sword and
Yep.
yeah, they kill themselves. Because the body is not in need of immune cells to attack self cells. That would, again, be counterproductive. Again, autoimmune disease is very interesting to study.
Isn't that something to do with cancer cells as well? Like that they attack like the mutated cell?
I don't know what you mean.
Well, like they're supposed to work to attack the mutated cell, but because it's a self cell that's mutated, I don't know. I don't want to get anyone confused, but when I did my paper on in AMP1, it was on lung cancer, and it was something along those lines, like that.
Okay.
Like how the cells know not to attack itself, and that's a lot of the reason why it mutates and spreads, kind of thing. But that's totally off topic. Go.
Yeah,
Forget I even said anything.
No, I mean, it's a good question. I don't know that I can comment on that.
Fair enough.
Okay. So we're taking these two cells out of the equation because, again, we don't need them. These other resulting 6 cells, however, have receptors that do not detect self. They detect potential non-self cells or entities, toxins, whatever. Is there any guarantee that these 6 cells are ever going to see action? No, it depends on what the antigen is that you're exposed to and whether it has the proper receptor to identify it. But you're flooding the system with lots of different possibilities, and those are the ones listed here. These are the possible repertoire of cells produced from that original hematopoietic stem cell. So here comes the antigen. This could be, again, a surface molecule of a bacterial cell. This could be a toxin. This could be any number of different things. It could be an allergen. It could be pollen you inhaled through your nose in the fall, or when you cut the grass last week and you start sneezing. You know what I'm saying? Antigens can be all sorts of things, some of which can cause an immune response. And this particular cell, of course, has the proper shaped receptor to identify this antigen. These other 5 are totally oblivious to that antigen. They don't know anything. They don't respond to that antigen. They can go about their merry way, could care less about it. This guy, however, is very aware of it. And as a result of docking, if you will, combining with the antigen, that can set up a scenario by which this cell ultimately undergoes rapid cell division to make more copies of itself, all of which can, of course, because they have the same receptor, identify more antigen. So all lymphocytes have the same receptor specificity, true or false? You better know this one.
False.
False.
Right. Okay. Other specific questions you want to ask? I'm not going to just drone on here unless there are other reasons to do so.
I just have a quick question about the immunoglobulin classes.
Yeah.
What slide am I on? 65. Should we know like all of the chart basically, or just have a good consensus of like the monomer, dimer,
Dimer.
dimer?
Dimer would be 2 M's.
Fair enough. But
No.
should we know like all the like the percentages and
Absolutely. No.
okay.
No.
Okay.
No.
Okay.
No, that'd be silly. I think what the takeaway of this slide is, Juliana, is the fact that as you look at the 5 classes of antibodies, also called immunoglobulins, or capital I, little g for short, right? IgG, IgA, IgM, IgD, IgE, those are the 5 classes. What do they all share in common? Is this sort of Y-shaped morphology, right? You see it repeating throughout the entire 5 classes. Now, some of these are a little more complicated, a little larger in size than others. Others have a rather interesting complex of these shapes, if you will, within the single antibody. So this is one molecule, much more complex, say, than this one or this one. And then the other thing to understand, and I talk about that leading up to this, is the fact that when you look at, let's say, IgG, for example, we have, and these are proteins, well, glyco, so part carbohydrate, some sugar in here, but mostly proteins. Where it says C and it says V. What does C stand for? Anybody? No? C. C stands for constant. How about V?
Variable.
Right. So when you look at IgG antibodies, there are an infinite number of IgG antibodies. All of them have the same Y-shaped structure. And when I say Y-shaped, I'm saying this is just a symbol we use. They're not little Y-shaped things floating around in your bloodstream. Okay, I'm not saying that. I'm saying that when you look at a symbol of the molecule, we're going to utilize that basic shape, if you will. Anyway, the constant parts of the molecule are exactly what it says. They're constant. They're consistent among all IgG antibodies. All of them have the same amino acid sequence here, for example. But what makes them unique from other subsets of IgG antibodies is their variable regions. And it says here, this is where the antigen combines with the antibody. So there is a physical connection between the antibody or immunoglobulin and the antigen, which could again be on the surface of a bacterial cell. It could be a toxin. It could be whatever is viewed as a non-self entity by the immune system. And so these antibodies or immunoglobulins are also, in addition to being secreted by plasma cells, which is a type of B cell, it says here they can also act as specific receptor sites on B cells. Okay, now do you remember earlier we talked about the T helper cell docking with the APC? Remember that? Yeah. Well, B cells also have to have surface receptors to identify antigen, don't they? And there's a whole host of different types of antigens, as we know. There's a whole host of different kinds of B cell receptors, as we know, and that's because of the variable component here. Okay, so this means it can vary from one IgG, one type of IgG antibody to another IgG. They're all IgGs, but they can respond to different antigens because of the variable regions being different. So again, Juliana, I'll pick on you. Your son or daughter to be is already getting IgG from you before he or she's even born. You're providing that important immune response, defense, I should say, not response, because he hasn't been exposed to it or she yet. But what you're going to find, as I hope you find this to be the case with your infant, that they remain remarkably healthy for the first 6 to 12, 10 months, at least our kids. It's like they're exposed to all these antigens. I mean, there's just, I can't even begin to count the number. Yet they're pretty healthy. They're eventually going to get sick. They're going to get, hopefully, not many middle ear infections and all that good sort of stuff. But it's going to be an important thing that you provide. You are providing him or her now. And then if you decide to breastfeed, you're going to be providing him or her with additional immunoglobulins, which will further promote a strong initial immune system for him or her, plus less colic and other issues too that sometimes arise with kids. Not to get personal or off the topic, if you can breastfeed, and it's not easy to do for lots of reasons, you're really giving him or her a good start in life if you can do that.
Absolutely.
Yeah. I should talk, right? But yeah.
From personal experience.
Well, my daughter.
I'm just kidding.
No. Yeah. Well, she tried and she succeeded, but it was hell on earth the first week or two. It really was hard. It was really hard. But if you can do it, give it your best shot. Is my recommendation. Okay, back to your question. No, you do not need to know all these columns and such. Just kind of get a sense of their general, shape as we just discussed. And then down here is kind of the important takeaways. That's why I circled these. I think you should know that IgG and IgM are pretty darn important in terms of providing, in this case, neutralization of toxins and different kinds of viruses. Some of these antibodies can circulate for quite a long period of time in the body. We're hearing now about COVID-19, people who've had COVID-19 and what we call active immunity. So they've gotten sick, but they've built up antibodies to that virus. Now, the question, of course, that everybody's wondering is, how long can those memory antibodies survive? Is it 6 months? Is it 10 months? Is it 5 years? It's probably not 5 years, but how long is it going to be, right?
Well, I was telling you I think like 2 labs ago, my parents had it in March of last year, and my mom just got antibody tested, and her antibodies are through the roof still.
Yeah, right. You did say that. Thank you for sharing that again.
Yeah.
So it's been 14 months.
Over a year.
Yeah. And so that's a very, very, very good sign, because the worry was if these antibody titers were to decline precipitously after, say, 8, 6, 10 months, and we don't really know for sure, but that's a good indication from your parents' data, that maybe this is going to extend much longer than we might have thought. I mean, I'd like to hear more information about that, but that's very interesting. So I would know the 5 classes. I would know that when you look at percentages, IgG by far is the most common antibody generally. Now, again, they're saying average lifespan 23 days. Wow, I mean, that's not very long, is it? But that could vary. Obviously, does vary because your folks have had it now for 14 months. These are the ones, again, Julian, that you're providing your infant, your soon-to-be infant, right?
Well, that's what I tell everybody. I'm like, I'm like upset I haven't had COVID. And they're like, what's wrong with you? I'm like, do you realize the antibodies I could provide my baby? Like, I wouldn't have to worry about it for a long time.
Well, yeah, but that doesn't mean your baby's going to be protected from COVID.
Yeah.
For a while, he or she might be, but he or she's never seen that antigen and therefore doesn't have the memory
Yeah.
that your folks have. Your folks have the memory
Oh,
built
yeah.
up. So if they get exposed to COVID in another year, which hopefully they won't, but if they do, they're going to have the memory T cells and the memory B cells to nip that virus in the bud before it causes any
Issues.
fever. Yeah, exactly. Right.
Yeah.
Yeah. And that's an important takeaway for the end of the chapter when we talk about the difference between active immunity and passive immunity. That's really important stuff there in section 15.5. And we can talk about that if you want, but you're going to see questions on the test about active immunity, passive immunity, natural, and artificial. You should know the differences between those. And I can not think of a better time to talk about that as we are hopefully in the tail end of what has been just a horrible pandemic. And you've all seen the news accounts in India where things are just really, really bad. Although I did hear something the other day about how cases appear to have plateaued, but they're still, what is it, 300,000 cases, new cases a day. It's still horrible. It's terrible over there. Other topics, slides. You should know how antibodies interact with antigens. That's important. Well, I'm surprised there aren't questions. Are you finding chapter 15 not too bad?
Well, it's a fairly long chapter. I'm still getting through it, but it's not the worst.
Okay, that's good.
I have a question.
Okay.
The B cells are kind of confusing. So they have to take in the antigen and then present it in a T cell. They both recognize it. I wrote down notes when you were talking and I was rereading my own notes, but I want to make sure I understand it.
Okay. So in order for a B cell to, well, let's put it this way. Let's see, where in the slide?
15.4 is where I wrote these notes down, but
15.4. Oh yeah, that's way back in the beginning of the chapter. On page 484, you wrote that down?
I don't know, it's on my slide, 15.4 immune activities of B cells. I wrote B cell docks with the T cell, both recognize the same antigen, release interleukin, stimulate the B cell. Did I write that down right?
Okay, let's go to this slide. Trying to think which slide to.
Just right there, that one.
This one, okay.
That's where I wrote it.
Okay. Okay. Let me see if I can find figure 1514. I think it's right up here. There it is. Okay. So let's look at this slide real quick. So here's the helper T cell that we met about 20 minutes ago, remember, a half hour ago. This was the one that came into contact with the APC. Okay. Here's a B cell that has, again, specific surface antibodies. So IG, remember, stands for what? IG?
Immunoglobulin.
Immunoglobulin, right. So these Y-shaped immunoglobulins are, in this example, acting as receptor sites for the identification of the antigen that is part of this microorganism. Let's pretend this is a bacterial cell. It has on its surface a molecule called an antigen, a non-self cell, right? Non-self antigen. This antibody is fitting into it, identifying it. Once it identifies it, then it will engulf it, just like the APC sort of does. In fact, this could act as an APC, and in some sense, it actually, that's what it's doing here. It's presenting that antigen on the surface of a class 2 MHC, just like the earlier antigen presenting cell does, and this is what it's doing, really. And here we've got a helper T cell, the same guy actually, that already identified that antigen and is recognizing it here. So here's the interaction of the helper T cell. Here's the antigen presenting cell, in this case a B cell. And what the T cell will then do is produce a bunch of different kinds of cytokines, which activates this B cell. So yes, the B cell must dock with the helper T cell, but these interleukins and various growth factors, these are the cytokines I was referring to earlier. This is what fires this B cell up. If it had not phagocytized the cell, presented the antigen, docked with a helper T cell that also is identifying that same antigen, and then produce these various interleukins and growth factors, this B cell could then not go on to differentiate into what are called plasma cells and memory B cells. And so that's what these different boxes walk you through that process. That's what Carolina was talking about earlier in the lecture today, right? Do we need to know these? And the answer, of course, is yes, you should understand what's going on. Because why is it important to have plasma cells made? Well, because look what they're doing. They're secreting antibodies against that original antigen. Now, how will those antibodies interact with those antigens? Well, that's what figure 15.7 talks about. In fact, it goes through, and I also talk about this in the Zoom lecture, summary of antibody functions, complement fixation, agglutination, precipitation, et cetera, et cetera. Check out that figure 1517. That's what antibodies do in terms of how they interact with antigen and render it neutralized. You can't produce copious amounts of antibodies unless you have plasma cells present. You can't have plasma cells present unless you have activated B cells. You can't have activated B cells, blah, blah, blah. You know where I'm going with this. What about these memory B cells? Are they helping to fight this war? Yes or no?
No.
You're saying that like no? Question mark?
Yes. Yes.
Oh, they are? They're helping to fight the war? How are they helping to fight the war?
Memory B cells would be for, well, after you fought off the infection, if you were exposed to it again, metaphorically, you can mobilize the troops quickly.
Well,
to
that's
deal with if
true,
it comes
but
back.
you're absolutely right. But the question was, can it help win this war?
No,
This
because
was-
they're waiting until
Yeah,
the next
not the war
infection.
it's currently in.
Right. It's not going to help win this war, But if the enemy attacks later, that same enemy attacks later, then these memory cells can differentiate into plasma cells, and the plasma cells can produce more antibodies much, much faster, right? So memory cells, be they B, which is what these are, or T, are there to provide memory of that same antigen should you get exposed to it later in life. It could be in 2 months, it could be in 2 years, it could be in 20 years. So circulating in your body, hard to believe this, are cells, B and T cells, that might have been born in your bone marrow back in 2001 or earlier. Isn't that pretty remarkable? And if you don't have 20-year-old cells, you have progeny of those 20-year-old cells that still have the ability to recognize that same antigen. So, Monica, does that help clarify that?
Yeah, I just want to make sure I wrote it down right. They dock together or something.
Yeah, yeah. What you're seeing here is the docking of the B cell with the helper T cell. That interaction, which you see magnified here, this processed antigen of the B cell being presented to the T cell, this helper T cell is recognizing that antigen being presented to it, and that's what triggers the release of these interleukins to specifically fire up this B cell.
Okay.
Yeah. Again, you can't activate the B cell unless it interacts with the helper T cell. That's where it gets the name helper, because it helps mediate the immune response. If you knock out the helper T cells, you actively prevent activation of B cells. I liken it to a bar stool. You've got 3 legs to a bar stool, right? If you cut off one of the legs, try sitting on the stool. You're not going to be able to. So if you start eliminating helper T cells, theoretically, as the AIDS virus does, and I talk about this in the Zoom lecture, AIDS is more of a chronic manageable disease now than it has ever been. But again, when I first started teaching a long time ago, AIDS was quite rampant in our world, mostly in the gay community, but also IV drug users, were targeted too because they were using the needles over and over again. The virus is getting spread via the bloodstream and all that. And still people die of AIDS today. I'm not saying that it's chronic all over the world. It is in the US, but you go to Africa and other parts of the world, AIDS is killing, I don't know, hundreds of thousands of people every year. It's not like gone. We don't see it. We don't recognize it. We don't understand how prevalent it is. Just like malaria, we don't hear much about malaria in the United States, but it kills hundreds of thousands of people in the world. So the AIDS virus gets in here and it replicates in the helper T cells. And so you're cutting one of the legs off the bar stool, basically.
Doesn't AIDS have to do with the CD4 plus T cells?
Say that one more time.
Doesn't AIDS/HIV have to do with the CD4 plus T cells? There's something like that. And so to be diagnosed with AIDS, you have to have like below a 200 on that inopportunous infection, and that's classified as you having AIDS.
Okay. Yeah, I would have to do some reading. I just don't recall. But you're right. The Cd4 receptor has a role to play in this too. Yeah.
And most people don't die unless, like, if they get treatment, like they get the pre-exposure meds if they think that they're at risk. Most likely, like as long as they like be safe and stuff like that, they're not going to get it. And if they've been exposed, if they get the medications for that and stick with the medication regimen, they should be fine.
Yeah.
But if they're like, oh, I don't have it, I'm not going to get treatment for it, it's most likely going to be a death sentence because your immunity sucks.
Right.
So,
you know, back in the 80s, the chemical that drug that was used most widely, and it still is today, but not maybe all by itself, was AZT. And I think we talked about AZT in one of the earlier chapters. Azithromycin, I think it stands for.
Yeah, they still use that.
Yeah. And we talk about a cocktail of drugs now. It's a whole host of different drugs that are given a regimen of those. But you're absolutely right. They have to stay on those meds.
Yeah, that's one of the first things. If they come in and say, like to the doctor's office, like, and they see that their CD4 T cell count's down, they're like, oh, well, are you taking your meds? Because that would be a reason why it's not.
Yeah. And depending upon who the patient is, it may be very difficult for them to stay on those meds, you know, be it lifestyle or whatever. Lots of reasons why people don't do what they're supposed to do. Maybe they can't afford the medication or don't have access to it. Yeah. That's interesting. Okay, we have a few more minutes left. Other questions related to 14, 15, or even 13, I suppose?
I don't have any questions. I'm feeling pretty good about it.
Good, good. Okay, well, I'll be around in my office for another 10 minutes before the micro lab starts. Feel free to hang around if you have questions or whatever. Otherwise, good luck on the test on Thursday. You guys have been troopers hanging in there remotely now for 15 weeks. I know it's been really tough for some of you. It's not my preferred way of teaching. I don't like to stare in front of a screen and see empty screens looking back to me. I get why it is what it is, but let's hope. And signs seem to be indicating that fall will be a more normal semester where you'll be in class, at least for some of your classes. I just saw yesterday that Governor Cuomo is mandating that all students returning to any of the CUNY or SUNY schools in the fall be immunized, or they won't be allowed to register for classes. I personally applaud that. The sooner we can get this toward a herd immunity situation, which again is discussed in the back part of this chapter, actually there. If you want to check out what herd immunity is, check it out, page 507. It's in that last section that I'm not going to lecture on. I'm not going to ask you about herd immunity, but I would just encourage you to check it out. Hopefully we'll get back to a more normal process. We'll never get back to our pre-COVID. I think there are some good things that have popped out of having to teach remote. Some of you, I hear, prefer the remote mode versus the in-class mode more. So maybe there'll always be some options of this sort of a style of teaching or learning. I guess it has its place for certain classes. I'm not always sure it is great for A&P and micro. I don't know. You tell me. We got a few minutes left. Anybody want to offer any commentary on how this semester's gone for you, whether it's in this class or other classes remotely? Are you looking forward to getting back to your classes? Are you liking this modality? Do you like the convenience of not having to leave your home and all that? Or I'm curious what your thoughts are.
I don't like it. I don't like online because I feel like, I don't know, I don't get as much out of it as I do in like the classroom, I guess. Like, I don't know, but I'm done pretty much. So thank goodness.
Yeah.
I feel like online classes are fine for certain classes, but in cases like math or, well, microbiology, you know, it's one of those cases where it really gives me too much wiggle room to do other things, and that's a problem for me. Yeah.
You like to have the schedule, the
Yeah.
Life always seems to get in the way when you're at home.
Yeah.
For sure.
Yeah. Oh yeah, I can only imagine, Carolina, when you have children that are like, you can't get away from them. They're there. You're going to give them priority, as you should, over your school work. I mean, gosh, you got to do that. And they're never going to be satiated, especially if you have an infant, right? It's hats off to you guys. I don't know how you do it. I just don't know how you do it. You wait until they go to bed and then you study. And by that time, you're so exhausted mentally and physically. Yeah, I mean, I can only imagine how hard it is. Right. Well, you know, I hope you've learned something. Obviously, you've learned something, I hope. You might retain only maybe 5%, 10% of what you learn. Isn't that what they say? If you're lucky, maybe you retain just a small bit of it. But at least you've been exposed to this field of microbiology, and we've just scratched the surface. And, you know, my training is not as a microbiologist. I never have claimed to be an expert on this topic either. I find it fascinating and interesting. There's always more to learn, and there's a lot to learn. But in today's world of COVID-19, there's no better time to learn about these things, I think, and appreciate them and be a better informed citizen. When you hear about things on the news and policies being passed in Congress or wherever, you know, you can make those decisions and inform those opinions based upon knowledge. And I think that's what college is for, right? It doesn't have to be biology. It could be history, it could be English, it could be political science. You're broadening your ability to make intelligent decisions. That's the whole idea behind school. And to expose yourself to other ways of thinking, right? So there's my philosophical approach. But have a great end of the semester. And if you have any questions, let me know. And have a good summer and all that good stuff.
All right, see you in 10 minutes for lab.
Okay.
Thank you.
Thanks.
Thank you.
You bet.